I would like to thank the organizing committee inviting me and to give me the chance to give a talk in this conference. Also, I hope that I will remain unknown. Actually, I am sorry that I am afraid that I won't be unknown after this talk, and you will see for an obvious reason. I hope it at least will not be scandalous. Also my language, but there is nothing wrong with my language. Yes, it's very international. Hungarian English is really very international language. We cannot say it about the English language because I am pretty sure that nobody understands them. They understand each other when they are among themselves, but other than that, very rarely. So I hope at least that there won't be any problem with my language. What I am going to talk about today is a joint work with my PhD student Simao Herdade. Actually, he's Portuguese, almost French. And the problem is the following. We will start with a set A. Let's see, yes, which is in the everything is integer in this talk, in the interval from 1 to n, and then you already know, you have heard a lot about it even in this conference. Then if you consider a minus a, and then we require that a minus a is square free, which means that there are no two elements in a, so that the difference is a square. And that was a breakthrough result of Endre and Sárközy, who proved that A over, that absolute values, of course, as always, is the cardinality of the set. So the cardinality of set divided by n is less than 1 over log n to the 2/3. And then about the same time, but slightly later, Fürstenberg gave an ergodic theoretical proof for that. But his bound was much weaker than Sárközy's bound, though he used methods which later became very powerful. But we can actually say the same thing about András's result too. And then in 1988, János Pinc, William Steigen, and myself improved a little bit András's result, namely that the cardinality A divided by n is 1 over log n to the log n. And then from Mate, as we heard the lecture, that maybe, and there is a very real possibility, then they will improve it so that the cardinality of A divided by n is less than n over e to the square root log n, and I really wish that they could do this. Now, well, but I wish, I still can wish. Okay, well, you are on the right track. So now, forget about, so you can see then the difference, yes, you can have a very small set, so that the difference doesn't contain a square. But now we turn our attention to a seemingly same problem, but only seemingly same problem. Namely, we are interested in the following problem of Paul Erdös and Endre Sárközy, dated from 1981. Then that we have an infinite sequence, so that A plus A is square free. It's just simply the same thing than there. Then there are no x and y in A, so that x plus y is a square. And at that problem, though it looks very similar, but is very, very different than from the problem when we consider the difference of two sets. And Why? Because here you see, here the density is very small. But, so they asked then what is the maximal cardinality of A, or how big A can be, what should be its density. And then a very natural first guess, which was, I am sure, their guess, so I have never heard it, but I am sure. Then X, that if A is X congruent 1 mod 3, then this is the densest set. So what is the density of that set? It is 1/3, yes, because 1/3 the element satisfies this. And I put a question mark here because I don't exactly know the story for that. And the other reason is then this is a wrong guess. Well, you can guess anything, but it was a reasonable one. And now I am in a real trouble because some of you are French. That wouldn't be that bad in general. But I cannot pronounce properly. I really tried hard. Then Massias, who is a French person. Massias, thank you. So please correct always me, either the mathematics or the language or any other things which you feel like should be corrected. So, and that he came up with a very surprising construction. I don't know how he got this idea. And then his set was the following. M26, you will see why I use this index here, 26, was the following. Then his set is the set of x's which are congruent 1 mod 4, and then also x is congruent 14, 26, 30, mod 32. So that is why 26 is here and 26 here. But actually, we found another example. Most probably he must have known the another example, only wrote down this one, M26, namely M10, which is then the same, it starts in the same way, x congruent 1 mod 4, but here x congruent with 10, 14, 30 mod 32, you see 26 has been replaced by 10. So therefore, we denote this set by M10. And then, how many residue classes we have here? Yes, 8, because x is congruent 1 mod 4. Yes, so then it's mod 32, it gives 8 residue classes, and then 3 more. Yes, 14, in that case, 26 and 30. So what is the density then? 11 over 32. Yeah, and then actually this is bigger than 1/3. So that is a very funny, strange construction. And one, most probably after that, would think then this will not be the right answer. And then what we are trying to do now, then to justify this, that this construction is the proper one. And I just will go through that what we are going to use, and then we'll state the theorems. So a beautiful paper of Jeff Lagarius, Odlisko, and Jim Scherer consider not the infinite, the version among the integers, but the modular. Namely, they consider a subset in the cyclic group of size 2 to the n times m. We assume just for simplicity that 2 to the n in this case is bigger than 32. The other cases are simpler, so, and so that x plus y is not congruent z squared, so it's not quadratic paradox. So if you take any two element in A, we already heard in this conference many lectures about this thing, so it's not quadratic residue. And then what they proved that the density of A, meaning that the number of elements is only 11, here it's not the density, the number of elements. So the size of A is less than 11 over 32 times 2 to the n times n. 2 to the n times n, I should, yes, is the size, of course, our cyclic group. So the density is 11 over 32, exactly the same as in, no, please help me, Matthias, thank you. Matthias example. Furthermore, what they proved is they also proved that if A is an union of congruence classes for a fixed modulus, because everything is union of modulo classes, yes, an infinite sequence, modulo 1, yes, everything is. But here you fix modulus, and then you take a union of some residue classes for this fixed modulus. Then, of course, it's a very special structure. Then they proved that the density, then the size of A is, well, here maybe we could talk about the density. Then the density of A, so A divided by N, the size of A divided by N is less than 11 over, less than or equal than 11 over 32. So in this case, they proved the Sárközy's, Erdős's conjecture, but unfortunately, they asked for a general sequence. And then later, they tried to prove the correct things, but they just could come up with the 0.475 for the general case, when we don't assume anything about the structure of the set. And then 4.7, this is actually bigger than 11 over 32. But on the other hand, let me just make a very short remark that, of course, 0.5 is trivial, yes, because you just take a square, take an x, and then because you have still half of the elements, so easily you find the third element, so that x plus y is equal to z square. So, but they got very close to it, and somewhat later, with my two students, we proved the following thing, that the size of A divided by n is less than 11 over 32, the same thing, plus delta, where delta could be any small. So you just choose a delta, and then the density will be less than 11 over 32 plus then for a set which, for which x plus y is never a square number. So this is an asymptotic result, and it's almost tight. But actually, there's a big difference between almost tight and between tight. Actually, if you really, if I could explain you the proof, then the proof much more complicated if we omit the delta than if we get this a little bit more room, namely that we have this extra delta. So that is actually not only the history, but we are going to use this result to prove that one, because I am not going to give a whole proof, but if I can get there, then I just would like to give some idea how to prove this one. Okay, any question, please? Well, I should have a question. So this should go up. Is the last row, can you see then I maybe should, no, this one, let's see how, if I get lucky that will be, no, definitely not, but this one, you can see now, okay. Now I will explain the theorems, and then after that, I will try to give some so-called ideas. So theorem 1 is the following. It's here. that if A is in the cyclic group of size 2 to the n times m, the same as previously, and then of course we always have this condition then no x and y, so that x plus y is z squared mod 2 to n times m, which means then it's not quadratic residue. Then from it follows that A is either M10, the definition of there, you see this strange. Now, third time I will not ask how to pronounce the name of the Messier. Okay. Massia. It's just Massia. I even cannot pronounce sometimes some Hungarian names either. Sometimes even my own. So, okay, I just will replace it's not nice with M-A. All right, so then M10, M stands just to really appreciate his work. M10 intersection the group. Or N26 intersection the group. So how many residue classes we have here? Exactly 11 over 32. Yes, so that is exact. Not only exact, but these are the two examples. There is no other, bless you, there is no other set which has the density 11 over 32. Okay, that is the theorem 1. And then unfortunately I had the wrong order, because actually mostly in graph theory, but maybe in number theory, it's also not only the tight result is important, but whether it's stable result. Meaning that if we somehow change the structure of the extremal set, then maybe we can say something more. And exactly this is the citation, but this is not theorem 3, yes, but it's theorem 2. I should have put this one here, so interchange, but anyway, you see, I knew that I made a mistake, so I wanted to interchange, but I just didn't have enough time. So theorem 2 says the following. Then A is again, as always, is in the cyclic group of size 2 to n times m, and of course the same condition, x plus y is never a quadratic residue, mod 2n times m, and then here, that is where starts the condition that A symmetrical difference M10 intersection Z to the 2 times. It's just that we consider the residue classes in the cyclic group. Now, what is a symmetric difference? I don't have to explain, yes? Then the symmetric difference of two sets, yes? It is that, okay. Elements which contained in one of them, but not in both. Okay, so if this symmetric difference is large, epsilon times, this is the size of our group, yes, or of our side group. So F bigger than epsilon times 2 to the m, or the same, because we don't know whether it's M10, or M26, the symmetric difference between A and N26 is bigger. Of course, we have to intersect with the, because we are also only interested in the elements which are in the group, which are residue classes. So that is bigger than epsilon times 2 to the, that is very bad, because M should come down here. Okay, you understand that the size is the same, 2 to the n times m. Where m is, of course, I forgot to say, is an odd number. So we just have the factorization of the number, so it's 2 to the n times m. So you see, if both symmetric difference is big, then if A, then there is a delta, so that A is not. So, well, if A doesn't have the, in this way I can also say, if in A we cannot solve x plus y is congruent to a quadratic residue, then A is less than 11/32 minus delta. And here epsilon can be taken as, let's say, 2 times square root delta. So what does that mean? Then once our set differs reasonably means then a positive percentage, then our set cannot achieve the required density, namely 11/32. A little bit less already enough to solve the equation x plus y is a quadratic residue. So that shows that it's a pretty strong stability result. And then now forget about, because it was only about the modular case, and then now we turn to the real question, at least to András's question and Paul Erdős's question, and this is theorem 3. Then A, well, we considered the finite version of it, because it was asked about the infinite sequence, but we just considered the finite version of it. And from 1 to n, we are interested in how many elements A can have, so that x plus y is not equal to z squared. This is actually equivalent or maybe slightly stronger, but it doesn't matter. So, theorem 3 states that if A is among the first n integers, this cannot be solved. Then, if A is of size 11/32 times n, then A is either m, whatever I wrote it, actually instead of 14 I should have written 26. So m26, because somehow, yes, 14 was there, sorry, and there is no such a thing, m26 intersection by 1/n. Or m10 intersection by 1/n. So you really can characterize then which is the set which assumes the maximum. And then, so that actually answers the questions of András and Paul Erdős. But we went, and then what is actually much more difficult, nothing so difficult here, but definitely much more difficult than this one, is theorem 4, which is the stability version of the theorem, and it actually sounds exactly the same as in the modular version. That if A is in 1/n, no x plus y is equal to z squared, and the symmetric difference, the same condition like in theorem, which one was it, 2. Then but now, of course, we have n elements, yes, because A is sitting in the interval 1 to n. Then if it is bigger than epsilon n, or for this one is bigger than epsilon times n, then A has to be less, the size of A has to be less than 11/32 minus delta times n. But again, the epsilon and the dependence of epsilon and delta is written there. So now we have all the theorems, and you can see that the exact theorem, I mean, and then also the proof that it is a very stable, and the very strong, in a very strong sense, the extremal set it cannot be perturbated, because if you perturbate it a little bit, then already it should be much smaller. Much smaller, of course, 11/32 minus delta. Okay. Now, so I will have to put it up. And then I will be actually very happy if at most half of the time I am going to make a mistake. And now I am about there, even less than half. So I mean moving this thing. Actually, I am completely left-handed, and I had to do everything with right hand, and it's really very, very disturbing. Okay. Some ideas, well, that is a little bit big word because there will not be any. So let's, we just want to present the ideas on this problem then when the density is slightly above 11/32. And then the way, yes? So what shall I do now? Less? This is better? Thank you, thank you. So, what is this shifting method? Well, we want to prove, yes, this one. For this one, then x plus y is not equal to z square. Yes, and then we want to give a bound for the size of the set which satisfies this property. Now we all know then to solve a particular problem is difficult or might be difficult. So instead of that, what we are going to do, and there is some small trick, then we want to solve not these equations only, but we will consider only, we will have an m. M will be a fixed number, constant, but it will be highly composite number. Why it is composite? Most probably we will not have a time to see this, why m should be such a strange what is here. Then so what we do, then we consider all these equations. It is a lot of equation because you see J runs from 1 to n to the 1 minus 2 epsilon. So really a lot of equations, yes? And then of course if you have a lot of equations, that is kind of averaging, yes? And then you hope then you can control the number of solutions of this lot of equations, because it's not only one equation, infinite many, and they are very nicely structured, because you always shift only by m, yes? So it's shifted alongside an arithmetic progression. But on the other hand, on a very long arithmetic progression, n to the 1 minus 2 epsilon. So, and everybody would guess then the number of solution, it is there, is exactly what we expect, the expectation, if they were random. That is not hard to prove, we will come to it, not where we lose some factor which is completely irrelevant. But most probably I will not have time to do this, but that is actually the idea behind the shifting method, so that this one, most probably with an easy combinatorial arguments, can be estimated. Then how many solutions we have there. On the other hand, well, I wrote it, now, that was the last one. No, this one, no. What is this? Oh, no, it doesn't work. So can you see this? This is the standard thing, that the number of solutions can be written, yes, in a very simple way as a product of Fourier transformation. Many times we heard about it even in this week. So for the number of solutions of the original one, if this is the Fourier transform, this is a Fourier transform set A, then the number of solutions of the first equation is exactly this. But SQ stands for the square. This is an identity which many times we worked with this. So this is absolutely standard. So look at this. But on the other hand, for the solution for this one also can be written in this form, except then because we have x plus y plus jm, so our second set is not a plus jm, right? And then the formula remains the same. So that is the second formula. But the point is, then if m is composite, then how do they estimate this one? That they estimate for a particular coefficient here, then t over 2n is that is just Dirichlet, minus a t over bt is less than 1 over bt times q, where q is n to the 1 minus epsilon. This is just Dirichlet. So this is how they approximate the particular places. Now, the whole point why M is composite, then if BT is large, then of course this one we know is Gaussian sum, so this is small. And by Parsifal we know that nothing changed or very little changed. On the other hand, if BT is small, then BT will divide M because M is highly composite. So nothing changed. This coefficient didn't change at all. So the coefficients which, so in this Fourier expansion, the terms where t over 2n is approximated by with small denominator rational number, then doesn't matter. I can multiply it by e to the j times m. Doesn't make any difference because m, b divides m, so actually I multiplied by 1. So I didn't change this term, the dangerous term. And the other terms, I have the Gaussian sum, so didn't change anything. And the changes, it's absolutely standard, is at most n times square root n over square root p. The square root comes because at some point we have a cut off point and then using Parsifal. So what is the message of the whole thing? Then, and that is the idea behind this shifting method actually, and can be applied many other places. For instance, for the first improvement for the Rho theorem was done exactly using this idea, from n over log n to the n over a to the square root log n. Here you see this is very small number, so therefore the number of solutions you just added is very, very small, much smaller than what we expect when we consider the arithmetic expression or Fourier transform expression. But on the other hand, we cannot get into this. This is on this right-hand side, that, but maybe 2 sentences. Then on our hand, we can compute the number of solution x plus y plus g times m. Why? Because look at this. Obviously, if we have a little bit over delta, then it should be a, b, and c, so that a plus b congruent c square mod qi. And then what we do is then, okay, take this whole thing is one congruence class, mod qi congruence class A, another is B, the third one should be C. And then take and then divide this into interval of strength n to the 1 minus epsilon, take 2 points, P, Q, and the last one, P, Q, and S, so that P plus Q is equal to S. But look, and now if I just shift it inside the interval, yes, I will hit very many times a square number, yes, because in that interval the number of square number is approximately n to the 1 minus epsilon divided by square root n. So I will get, I add everything up, and I will get the average. Maybe I lose something qi because everything is mod qi, but it doesn't matter, because here you can see that this is constructed, m is constructed in such a way that the last prime, the largest prime in the next one is much, much bigger than q to the j to the 20. To the q in the last prime in q to the j plus 1 is much bigger than q to the j to the 20. So therefore, if I divide it by square root p, this is very big number compared to qj. And here our loss is that q to the j to the 5th, which is nothing. So therefore, there is a contradiction. Combinatorial wave, easy. This is real easy, just shift. 1, 2, 3, and then shift it. And you see how many solutions you will have. The number of squares in this interval, just the average. So then this one is easy. That one also is easy to estimate, but the two estimation doesn't add up, right? One of them is much smaller than another one, though both computes exactly the same thing, namely the number of solution of 1, x plus y plus j times m to the z square. So that finishes the whole proof. Of course, if delta is not there, then you have to do some tricks, but still the shifting will be there and will play an essential role. So I guess that I cannot say any, and then of course it doesn't have to be a square, so you can apply the method for any function, and the shifting methods works for that too. Thank you very much. Actually, I should have written, and I will do, and that hopefully readable. Thank you very much. I still have 20 minutes, seconds, very much for your attention. Thank you very much. Thank you.